everyone, today we are talking about patterns in functions. We have spent a lot of time in this course trying to find patterns in bivariate data. In this last unit, we got one more common pattern for the data. We will look at exponential growth and decay and their inverse function called logarithmic functions. Example number 1. Try to find the pattern in each of the following and fill in what the next output will be. So let's take a look at example A. If you take a look, year since 2000 is going up by 1 year. Price in dollar, if you take a look, it's going to be going up by 5 and then going up by 5. From the previous lesson, you should know 22 is going to plus 5 and give you 27. And then describe the pattern in the output value, and it's going to be it increased by 5. So the pattern I put down for example number 1 is the output value increased by 5 per year. Example 1B and 1C. And we will discuss the answer when you guys finish. So for example B, year since 2000, price in dollars. If you look at the pattern 1 to 2 went up by 1, 2 to 5 went up by 3, 5, and then so forth. So therefore it went up by odd numbers. Letter B, when they say describe the pattern in the output values, I said the price increased by adding odd consecutive numbers every year. So in this case, the first year you add by 1, and then the second year you add by 3, and then so forth. The ones that we want to find out the answer is actually adding by 9. Letter C, if you guys look at the patterns, 3 to 6 is went up by 3, 6 plus 12 it went up by 6, and then 12 to 24 is you adding 12. So to me, the price doubled every year. That's the same thing. 48 double give you 96. So that is example 1. In previous chapter, we have looked at data that were related through a linear function, which is a straight line, a quadratic function, which is a U shape. This chapter, we are going to look at data that are related through an exponential function. Once again, we have some foundation to build before we get there. To example number 2. Example number 2, use the input-output table below to answer the following question. A, what is the pattern in the given output value above? Well, the pattern in the output value above, which is doubling, which is letter C, the pattern is just double on the output. Above right here is doubling the output every year. So B says use the pattern in the given output value, fill in the missing output value. So we are going to fill this chart, and you guys think about the pattern and then see, can you guys fill it out and answer the question, and we'll come back and discuss it. For example number 2, letter B asking to fill out the missing output value. So here's what I did. I say 16 divided by 2 give you 8, divide by 2 give you 4, divide by 2 give you 1. Then you divide by 2. Right here. Now I would like to write this out for you guys. If you have half divide by 2, that's the same thing as half times 1 over 2, and that's give me 1/4, and that is where this 1/4 from. And then we are using the same idea every single time, and then the number would just be 1/8 and 1/16 because it is divide by 2 is like multiply another half. That is where I get those numbers. C asks how are the output value for the input value of 1, -1, and 1 related. Here's 1, here's -1, it's 2 and half. How about the 2 and -2? 2 is 4. -2 is actually 1/4, and then 3 is 8. -3 is 1/8. That's why I put down. The numbers are reciprocal each other. That means it flip. And D, what is output when the input is 0? The input is 0 right here, and the output is 1. There's your question. That's example number 2. Example number 3, the cost of a movie ticket in a large city has increased exponentially over the decades since 1953. When records were first kept, a function that models the cost C is given C equal to 1.25 parentheses times 1.5 to the D power. So now they are asking for A, computing C equals 12. That means the 12 is going to be going towards D, because usually you go C with a variable in the middle right here, and that is in response to D. So if D equals 12, we need to plug in the number. And please do the calculation, use your calculator, and then double check back with the number just to make sure you punch in the calculator correctly, because there is an exponent right here. So order of operation tells you exponent gets done first, just in case you don't have a more order of operation calculator. Then we're going to talk about the interpret C sub 12 in the context of the problem. In computing c equals 12, the 12 has to go into the d position. So it's 1.25 times 1.5, the 12th power. And when you punch in the calculator correctly, the answer should be rounded to $162.18. And the reason we're going to 2 decimal places is because we're talking about pennies. So that's the first one. Second one, B, interpret C12 in the context of the problem. Well, since D stands for decades, so in 12 decades, the movie tickets will cost $162.18. Now, if you kind of say, maybe it's not decade, maybe it's years. Well, since 1953, the years is going to be 1965. There's no way you can have $162 for the tickets. So that's why it should be decade in 12 decades, and that's 120 years. So just so you know, 120 years, the movie tickets will cost $162.18. 6.2, the objective is going to really talk about exponential function. We just laid the groundwork and the foundation before. So let me read the graphs for the exponential function is going from small real quick all the way up, going really fast, or going from really fast and just dies down. So in this case, it says an exponential function can model growth. The value of the function rapidly gets larger as x increase. So x increase and then gets faster. And the exponential function can also model a decay. So model decay is going to go really high and go down really fast. The value of function rapidly gets smaller as x increase. The growth and the decay starting now. Evaluate expression 3 times 2 to the t, and t is going to be 0, 1, 2, 3, 4. So I'm going to make a chart. Number 1 says, what do you notice about output? A says, what do you notice about the output above? And the answer you get, for example, number 1, the output is doubling every time when the t is by 1. Next thing, the relation between time elapsed and the number of bacteria can be described with the following function. N function of t equals 3 times 2 to the t power. This leads us to a new family of functions for this unit. That's called the exponential function. And the definition of that is an exponential function is a function whose equation can be put into the form f of x equals a b to the x. To the x is the exponent. Where a cannot equal to 0, a has to be 1 or negative. Okay, a cannot be 0, and b has to be greater than 0, and b cannot equal to 1. Right? B cannot equal to 1 because if b equal to 1 right here, there's no way you can raise the power. B will be something else, and then so we're gonna spend a little bit of time talking about that. Going on to example number 2. Example number 2. Compare the linear and exponential function table below. Describe how m and b, that's a line, in the linear equation, and a and b are related to the pattern in the table of the data. So if you look at it, you should notice the slope from here to here to here to here to here to here. It goes up by 2. So therefore, that's 2, that's 2, that's 2. It's 2 over going up 1, 1, 1. So slope is going to be 2 over 1. Now why? Well, because this is the y value, this is the x value, and m is equal to y over x because it's the difference over the difference. So you can just, I already find the difference right here. There's my difference. So I'm just going to do 2 over 1. Or you can do 5 minus 3 over 1 minus 0. 5 minus 3 over 1 minus 0. It's the same thing. So put down the equations. Y equals mx, which is 2x plus 3. Why 3? Well, 3 is the y-intercept. So that's why I'm going to use 3. And that's y-intercept right here. So the pattern for the exponential function, the equation was given to us at the previous problem, which is right above it, right here. So I just copied it down. All right. F of x, because I used this guy right here, and that's equal to 3 times 2 to the t power. Well, we're going to talk about what that means in the problem below. So I would think the 3 is going to be my initial value. So I'm sorry, my 0. Well, 0 is 3. Well, that's where the y-axis. So in this case, when x equals 0, y equals 3. So that will be the y-intercept. Think about this. T equals 0. 2 to the 0 power is 1. And times 3 is going to be 3. 3 times 1. Let me write that down. So now let's take a look at what they're really trying to tell us. What they say is write an exponential equation giving the table of value. F of x equals a times b to the x power. What does AB stand for? A stands for the initial amount. So there we go. That's the y-intercept. So therefore, you have to look for x equals 0. Then you're going to find y-intercept. Then the next thing we're going to do is we are going to find the common factor. I believe the common factor is how do they multiply from here to here. So 3 times 2, 6 times 2, 12 times 2. And that's how you find the multiplier. That's what that means. All right. So now let's take a look at can we come up with the right equation. So let's do the first one together. That's A. All right. So you know your initial, your A is going to be 7. And your B is going to, let's take a look. Multiply by 2, multiply by 2. So multiply by 2. So my multiplier is going to be 2. So it's going to be 7 times 2 to the t power. Multiplier is 2. So the function is going to be f of x equals 7 times 2 to the x power. That's your function, and you're done. So please give a try with B, C, and D, and come back and check your answer. For B, my A is going to be the y-intercept, which is 8. And B is actually, it went down by multiply half. I multiply from A, multiply half is 4. Multiply half become 2. Multiply half to become 1. My 8 is the initial, and the multiplier is by half to the x power. Same thing, C, A is 4 initial, and B is the common factor. So it's 4 times, so it's initial times common factor to the x power, 4 times 3 to the x. Same thing, letter D. A is 2, B is 4, f of x is equal to 2, which is initial, times B multiplier to the x power. And that concludes 6.2's notes.